Welcome to exploring the structure of multi-layer perceptron or MLPs. This is experiment number 1, binary networks. Exploring the structure of MLPs will be a series where I conduct experiments on MLPs. However, I do not guarantee consistent schedule. This is the weight matrix of a layer in an MLP trained on the MNIST handwriting digit dataset. The MNIST handwriting digit dataset is a dataset of handwriting digits and digits label. It is used to train MLPs on recognizing the digit through the handwriting images. The right part, which is the same layer, is trained on the same dataset with the same seed. A seed is basically a standard for a pseudo-random algorithm to generate random digits around it. So with the same seed, you can reproduce many randomly generated phenomenons in multi-layer perceptron and its training. But before we dig into the details, we need to discuss something. What is an MLP? So if you already know something about MLP, or you're just curious, or you just didn't know anything, you can watch this part. But if you already knew enough, you can skip to the other part where I introduce you to my research results and experiment. So an MLP is basically multi-layer perceptron, as a network consists of 3 parts: neurons, weights, and biases. However, this video only requires knowledge on weights and neurons. The network can generalize and learn tasks. These are 2 neurons without any connection with each other. The neurons can stand for anything. But in this case, let's just say we want MLP given an XY coordinate of a pixel in an image to predict RGB value of the pixel on that coordinate without showing the image when running it. The input neurons are labeled as X and Y, and output neurons are labeled as R, G, and B, which stands for red, green, and blue. And combined, it can almost make any color in the color spectrum. Now, I do not think anybody can predict anything with 5 non-connecting neurons, right? So we add more neurons. Now we added 4 neurons to the network. Notice that there's no labels. Now we will proceed to connect the input neurons to the next layer. The neurons without labels are called hidden layers, because unlike input layers and output layers, which we know the function, the hidden layers do not have a specific or general analogy to what the neuron is actually doing. For example, we know that the input neurons stands for the position of the pixel we want to run the MLP through, and RGB stands for its red, green, and blue value. But we have no idea what the neurons in hidden layers are doing. It can be a mix of things. This is the full network, with input layer and output layer fully connected through hidden layers. We label the connection between 2 layers by, firstly, the number of neurons in the first network by the number of neurons in the second network. We call that 2 by 4 because if you times it together, you get 8, and there's currently 8 connections between this input neuron and these first hidden layer hidden neurons. As you can see here, 1, 2, 3, 4, 5, 6, 7, 8. it can be represented in a matrix because these connections can have varying strengths with actually allows the network to have a variety of outputs given some very close input. Now, it's the same for all other hidden layers, and also the output layer, it's 4x3 because as you can see here, there's 4 neurons connecting 3 neurons, therefore there are 12 connections here and 16 connections for every hidden layer and 8 connections here. But now, what is a matrix? Well, a matrix simply put stores data just like an Excel sheet. Its size consists of 2 parts, columns and rows. By the way, if you are constantly mixing up the idea between columns and rows, here's an analogy. When you're rowing a boat, your pedal goes forward and back towards where your boat is headed. Imagine the matrix as a boat and you're looking at it from the top. Rows should be in the either direction where your pedal is rowing. We describe the size of the matrix as its rows by its columns. So this matrix is the 3x2. This is matrix multiplication. It's a kind of operation between two matrices. The first matrix is commonly referred to A, and the second is B, and we will do it the same for now. Now, notice that the columns of the first matrix need to be the same as the rows of the second matrix. This is because the operation is quite weird. One way to think about it is to rotate the second matrix 90 degrees anti-clockwise and place it on top of the first matrix. Note that if the column of the first matrix does not match the rows of the second matrix, this operation will not work. Also, the result of the matrix multiplication will be 3x4, or the row of the first matrix times by the columns of the second matrix. It's only the size, but not the answer. So now we're going to compute the answer. The computation is quite weird, despite the fact that it's already very weird. So first, you notice that for the first row, it actually takes the first element here and times it by the last element of the rotated matrix on the same left corner, and also it did the same operation for the other elements too. And now we move it and restore the numbers here. But notice that matrix B, or the second matrix here, isn't restored. For now, we will just take 2 times 3 plus 3 times 2. Now, we will take 2 times 1 plus 3 times 4. And it's the same function for the last one. After the last one was evaluated, we simplify all the operations so that it becomes numbers, because it is just arithmetic. And now we restore the second matrix. But for the first matrix, we actually take or remove the first row because we have already computed the first row of the result matrix. And now we do the same for what has now become the first row. Now that it's done, we simplify the arithmetic operations and we remove another another row from the first matrix and restore all the elements from the second matrix. Now we are just left with the last row, and we will do the same operations as all the other rows that are in or was in the first matrix. It's basically like repeating the steps. And finally, we are done. This is our result, or the product of the two matrices. And we can verify the size, and the size is actually checked out because 3 here is the number of rows in the first matrix by the number of columns of the second matrix here. Now that we know something about matrices, we can represent the connections or strength of the connections between layers as its own matrix, just like this. Now every number here are random. Yep, you've heard me. It's random at first. The hidden layers have the same value here because I'm too lazy and I don't really want to write a bunch of random numbers for each matrix. So basically, each random number ranges from -1 to 1. That's kind of the only boundary for the weight or the strength of the connection. As you can see, every weight matrix, these are called weight matrices, corresponds to what we've talked about as the connections and its strength. So basically, the connections between neurons and its strength is the weight matrix. Now hold up. If if multiplying all these together gives us the result, where can we input it? Well, there's two ways to think about it. The first way is that we add a dummy neuron that connects one neuron to the X and Y neurons, so that we have two weights or two connections that we can change. Or other way you can think about it is that the X here is actually the initial value with X, and Y is the initial value for Y. I liked the initial value approach, but if you want a more generalized approach, you can use this one too. Let's try evaluating this network when X equals 2 and Y equals 3. First, we do the matrix multiplication for the 1 by 2 and 2 by 4. Note that the column of the input is the same as the rows of the input matrix, which matches our description of the operation and its rules and restrictions. Now, because the shape is different, it looks kind of different, but it's totally the same. At first, it's 2, 3, right? And you times it by the last row, you get 1, okay? And then because it is 1 by 4, and these two match, so the output must be 1 by 4. So then we continue to do it. Note that like 0.3 and negative 0.2 drops down with the original value of the 1 by 2 matrix here, which is 2, 3. Now we got a 1 by 4 matrix. This represents the value for each neuron in the first layer, because there's 4 and there's 1 row. Now we will continue to multiply the next layer with the neuron values. And now these stands for the values for this one. And then we do it until we reach the end of the network. You can really see how the values propagate throughout the neural network here. And then finally we got a 3 by 1, which just clearly stands for the RGB value. But if MLP is actually firstly randomized, it shouldn't perform well at a task at first because it doesn't know the image yet, and it's randomized. So how does an MLP actually learn the image? Well, we'll go back to the more abstract analogy with the neurons and connections. The whole thing about learning is based on the MLP's laws. For example, if we look at the output of this MLP, we know that the pixel at 2, 3 over here is surely white, but it gives us a kind of middle number. Note that -1 stands for 0 and 1 stands for 255. So actually, the pixel at 2, 3 must be 1, 1, 1. Because if 1 stands for 255, it's 255, 255, 255, which we know stands for white. The loss is really just a function to evaluate how much the real output is different from the predicted output. For example, the real output of the model, if it performs very well, it should be 111, right? But it's negative, it's like this bunch of gibberish. So it actually just maybe a distant function or maybe some other complicated methods it calculates how much it differs, or in simple terms, how wrong is the network and how right is the network. After the network knows how wrong or how right it is, it uses back propagation to change its connection strength one by one, each connection by a time, until that it actually matches or there's not much difference between the real output and the the output that he predicted. For example, if maybe this weight caused the output to become negative, the backpropagation might adjust it so that the next neuron will be positive, so that it gets closer to 111 because 1 is positive number. In simple terms, backpropagation tries to minimize the loss function because the less the real answer differs from the predicted answer, the better the MLP is. I want you to think about that. Now we'll talk about epochs. It is a hyperparameter, meaning that it's defined by humans and will not be tuned in backpropagation. Epochs is basically how many backpropagation a model does. Ideally, the more epochs, the more the model perform better, but it might overfit. We'll talk about overfitting later. Basically, if you think about it, it has another thing to do with batch size, but we'll talk about it later too. Epochs, basically, if batch size is equal to 1, then it only evaluates one of these pixels, and if epochs is also equal to 1, they only evaluate one of this pixel, evaluate the loss function, and then just only change once, and that's your learned network. But actually, you can't really, the network, it won't make sense that it will instantly learn anything. I mean, it would make sense, but according to math and science, it is just not how it works. Of course, we wanted to learn everything in just one go. That would be perfect, but it's just like in the world, nothing is perfect. Now we will talk about batch size. So batch size is also a hyperparameter. It basically states how much data you need to calculate the loss and average before backpropagation. So the bigger the batch size, the more pixel it will get, the more pixel it will run and get the loss, so that backpropagation knows like overall how does the model process pixels. For example, the last time I said batch size equal 1, it will just process pixel 1 pixel each epoch. But it's like 512, it processes 512 pixels every each epoch. Now, the best, or not the best, I don't know. It's different for applications. Is for the batch size to be in the exact dimensions as the image here, so that every epoch it actually goes through every single pixel and takes the average of the loss for every single pixel, so that the backpropagation can change or tune the weights more efficiently and more precisely. But the more batch size you evaluate, the more slow the model learns. Because, for example, if batch size is equal to 1, it only needs to evaluate 1 pixel before it produces before it's called 1 epoch. But if batch size is 512, you need to run 512 times, 512 positions through this network. And because computers are not good at matrix multiplication, it is kind of slow to do that. So it comes in a cost of computational speed. Learning rate is also a hyperparameter. It just simply states how much will backpropagation change the values in weight matrices. So imagine that you are trying to knock a golf ball into the goal. A small learning rate means that you use very small force to push the ball, meaning that the loss didn't go down that fast. But if a large learning rate, you might actually see the loss go down quite a bit, because at first, if you use great force to swing the club, the golf might likely travel a big distance and land nearby the goal. But if you try to swing with the same force nearby the goal, it's not going to work. It's going to overshoot. So it's basically very essential to get the right learning rate. And mostly we decrease the learning rate, like as one plays golf. The closer it is to the goal, the smaller force you use to get more precise movement. Finally, we'll talk about overfitting. When an MLP overfits, it's just hard. It won't understand the idea. It will just memorize everything, every detail in their weight matrices. For example, if it's trained on an MNIST digit handwriting digit dataset, it will remember every single digit, what it looks like, and its label. But if you add a new handwriting image to that add a new handwriting image to run on the model that is not in the original training data, it will not know what to do because it's not in his lookup table. So how do we know if a model overfits? We use training loss and validation loss. Training loss is basically, for example, for MNIST, there's a training dataset of handwriting digits, and there's a validation dataset of handwriting digits. The validation loss handwriting digits, although with the same digits, have different kind of style in handwriting the digit, and that doesn't overlap with the training dataset. So if it actually overfits, we should know because it will not know what to do with the number before seeing data in the validation dataset. So the best thing is to have validation loss as equal to training loss as possible and training loss as low as possible. Now we will get into my main experiment, binary networks. These are layers of my MLP. The in features states the input neuron count here, while the app feature states output neuron count here. You can think of it as the shape for the weight matrices. The loss is made up of two parts. One is the cross entropy loss here. The other is my own function that encourages the model to make its weight either to be -1 or 1, or the binariness of weight matrices. Just to avoid any confusion here, binariness in this model doesn't stand for 0 or 1. It stands for either 1 or -1, because that's how a model actually understands. It is its kind of number system. The function is relatively simple. It's just a math equation. The most important part is here. And the most important part, other than the important part, is here. Now, let's just see what the function is about then. Actually pretty easy, it's just cosine, graphing it. Yeah, normal cosine behavior. But if we zoom into -1 and 1, we see that as the x value gets closer to 1 or -1, the y value drops on both sides, meaning that its value will be 0 at -1 and 0 at 1. So what does it really do for the training of the model, and why is it so special to be included in the loss function? Well, it's pretty simple because since it's made of two parts, cross entropy loss and my own loss, it actually needs to make sure that the cross entropy loss is low, and also my loss is also low. And how do we make our loss low? Making our weights closer to -1 or 1. That's how I ensure binariness. It's kind of close to reinforcement learning, but reinforcement learning actually tries to maximize the reward, so it's kind of different. This is the outcome compared between a vanilla MLP and a binary MLP. As you can see, I sacrificed a little bit of accuracy for the sake of binariness, but outcome is truly interesting. This is the binary layer. So this is the layer number 1. It's the input weight matrix. It's 784 by 128. It's pretty interesting. if you were to compare it. This is the weight matrix of the first layer in the hidden layers. It's 128 by 128. This is the weight matrix of the second layer in the hidden layers. It's 128 by 64. This is the output weight matrix. It's 64 by 10 because it was a 64 by 10 because the 10 neuron stands for the 10 digits. This is the input weight matrix of vanilla MLP. You can see that it's very different. This is the weight matrix of the first layer of the hidden layer in vanilla MLP. Very different also. The weight matrix of the second layer in the hidden layers of the vanilla MLP. Very different also. And this is the last layer. Very different also. I mean, like, the last layer isn't that different, but the rest of the layers are pretty different. Now this is the weights lined up side by side. Now we'll dive into my main experiment binary networks results. What I found? Something new? Yep. I'm sure I did, but just like someone might reinvent things, I might not be the first person to discover it. So this is a custom tool I made to make changing and experimenting MLPs easier. Link in the description down below. The test accuracy is the accuracy in the validation dataset, and the top part with the digit 0 to 9 are the accuracy for each digit. This is the first hidden layer, and the first hidden layer, not the input layer, and it consists of 3 parts. First is the vertical strips. Second, horizontal binary strips. Third, non-binary parts. Now what I found, which is astonishing, is that the vertical binary strips do not affect the accuracy of the MLP. So it brings up a lot of kind of possibilities, since it's true for all, or true for only hidden and output layers, in that you can possibly create copyright patterns here, so that ensures that others didn't really copy your model somewhere. You can create artwork here. There's so much applications that you can bring into this, but it's just for MLPs. I do not know if it is true for transformers, at least a transformer block, because we know transformers are also made of MLPs. We won't talk about it in depth this video. To prove this, I changed the value for every single vertical pillar in every layer. I lost the footage for all the other layers, but this is the first layer. I changed to random kind of colors, and it really didn't change the test accuracy at all. And it's same with hidden layer number 2 and the output weight matrix. However, if the horizontal binary strips is changed, the model will only give a few certain labels for all datasets. For example, when this strip is changed, it refuses to output anything given the generated dataset other than 8, which is very fascinating, and it's also true for all layers. Now, also if the non-binary part is changed, accuracy decreases. But it's not as dramatic as the binary horizontal strips. Now, it's also true for all layers. Lastly, we want to talk about the input weight matrix. I know it's not chronological per se to do it, but it's kind of an outlier because changing the horizontal binary strips don't affect the accuracy, and there's no actually no visible vertical binary strips, which is just bizarre. So basically, you can create patterns for each different layer, and just wow. And thank you for watching. If you like my work, consider subscribing. It's free and it means a lot to me. And that's the video. Have a good day.